Hey everybody, this is Larry. This is me going with Q4 of the weekly contest 347, maximum strictly increasing cells in a matrix. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem. So this one, it's tough. It's at the surface, or at a very basic level, it's longest path in a DAG, or which is in other words, it's like longest increasing subsequence or something like this, but in a two-dimensional kind of way, and it's a DAG, right? So what jumped at me is that it's going to be dynamic programming. But the problem is that you can't do a naive dynamic programming of like, okay, let's check every edge, almost similar in a way. What's going on? Almost I'm sorry if you could hear it. My neighbor's doing something weird. Almost similar in a way in that in longest increasing subsequence, it's going to be n squared if you're really naive about it, but you can reduce that to n log n. So the idea here is that, okay, if you calculate, the idea is that you always want to be greedy. Part of it is that to minimize the number of cells is that you want to be greedy because basically, let's say in this particular case, you have 1, 2, let me draw it out real quickly here on the ASCII art. Let's say you have, this is on the same row or same column, doesn't matter, right? Let's say you have 1, 2, 3, 4, 5. Well, the thing is that, yes, there's an edge from 1 to 5, you call it that. So you can go from 1 to 5, but never makes sense, right? Because if there's smaller numbers in between, you can also just go from 1 to 2 to 3 to 4 to 5. So it always makes sense to only just go to the next biggest number. And of course, it has to be strictly bigger because I guess it would just be infinite loop otherwise. But also just, complications, right? So that reduces the search space a lot. The other thing that is a little bit troubling is, let's say you have, something like this, or worse yet, something like this. The thing is that because pretend that we have ... on the columns, right? The answer for this 2 can be different from the answer from this 2, can be different from this 2, and this 2, and so forth, right? So in theory, naively, and you should do this in some way, of course, going from this 1 to all these 5 2s, you have to check every 2, right? At least once. But if you are not careful, if every one of these 1s check every one of these 2s, then now you also become like some n square thing, and that also is too slow, right? You have a linear array and it's 10 to the 5th. So basically, those are the factors. But once you realize that those are the trick cases, it becomes easier in how you attempt to solve it and just what you're caching on, right? So that's basically what I'm going to say. So let me go over my code and maybe that'll be more clear. And yeah, so first of all, I basically put all the rows and columns with the value and the actual column, the other factor, so that we retain all the information because we have x, y, and matrix of x of y, right? And same for the columns. And then I just sort them so that this allows us to get the next element much quicker, as you will see. And then this is my caching things for memorization, and you'll see in a second. But skipping the dynamic programming part for a second and going to the end, basically we just calculate, okay, what is the best cost? What is the best cost at xy, right? And that's basically the idea. And like I said, in the 1 case, right, it's still going to be n squared if you naively loop over it, even if you memorize it. So you're going to get TLE there, so you can't do it that naively. But, for now, we can just say, okay, let's just calculate xy and do our thing, right? Let's say we're starting from xy, what is the best path, and then we maximize over it. So this is going to be a little bit of a tricky part. So naively, you would write it a little bit differently in the basic, if you call it, dynamic programming. But now that we're more familiar with it, and we know that we want to cache. So the way that we're caching instead is that, for example, if you have 1, 1, 1, 1, 1, 1, 1, and 2, 2, 2, 2, 2, 2, 2. something like that, and it's going to be n squared and sad and slow. The thing is that, okay, so this 2 has a different answer to this 2 has a different answer than this 2, dot, 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 right? But every of these ones will always look at a 2. Like you cannot skip to a 3, or the way you set up, it shouldn't skip a 3 because the optimal answer will always contain a 2. Yeah, the next answer will be a 2, or the next thing in the chain, right? And so you can basically just cache all these 2s together, or all these 1s together, depending on how you want to say it. And that's basically what I did, right? I basically combined, all 2s on this row has answer X, or something like this, right? So that's basically how I start caching it, so that now this only has an O of 1 lookup because it looks up this and it gets one answer. This has O of 1, this has O of 1, and so forth. So that's basically the idea that I did. Yeah, and I do it for both rows and columns, as you can see. Yeah. So I set it the best equals 0 if I already have this value. So I look it up from the one's perspective, which is that for given X, if we already solved it for this current value, then we already know the answer. Otherwise, we just actually do the calculation, and including this for loop of just going through all the identical. So stepping back a second, so we do a binary search to get the next biggest number. We get the first index, and then while the value is the same, so while, for example, in the same example, if we're looking at if the next number is 2s, and if all the numbers are 2s, or like we keep on going until all the numbers are like exactly 2s and not go bigger, and then we calculate. And then the best row is you go to the max of just going to that row, or that cell rather, and then best row again. We take the max, and then we just kind of loop through it, because we only go through it for each cell, once for the row, once for column. This is going to be, we only look at each cell over 1 time, so that's good. So yeah, and same thing here. So you amortize all the costs for the rows and the columns, and therefore, and I did a kind of manual memorization. You can also rewrite this a little bit so that it's another function that you could just plug in memorize. But I thought this way is a little bit more how I was thinking about it. But yeah, so this is going to be linear time, linear space as a result. Maybe a little bit more expensive, to be honest, because of but I think that gets amortized out. So because you only do actually maybe not. Maybe there's a log n factor, so maybe I'm wrong on this one because of the bisection. But you can actually eliminate this bisection if you really want to keep it linear time, linear space, because after you sort it, you can think of it as a linked list, and then here you can just kind of do it that way, maybe, and then cache it or something. But in any case, doesn't matter. Yeah. And also there's a sorting here, so maybe I'm wrong on the linear time anyway. Not maybe, I'm wrong on the linear time anyway. So there's sorting, so it's probably R times C times log RC or something like this. But yeah, let me show you the top again. Like I said, this is the setup, this is the bottom, but the meat is this memorization, and memorizing in a specific way is how I did it. There are some optimizations here and there, but yeah. That's all I have for this one. Let me know what you think, and you could watch me solve it live during the contest now. Okay. Oh, I'm just being dumb today. Okay, fine. Maximum strictly increasing cells in the matrix. Okay. Okay, so you can go up. It's just longest path in the DAG. Right. Oh wait, am I missing something? Oh, same rows. I thought it was just adjacent. All right, let's think about this a little bit. How are people doing? People pretty fast, I guess. Wow, people are already done. I haven't even finished looking at it. I spent a long time in Q3 because of that silly mistake, or a couple of silly mistakes. People are pretty fast. Okay, focus. Hmm. Hmm. Is it, well, it is definitely a DAG. Is it just by first search? No, I mean not quite like that, but well, if everything is the same row, we can always go up anyway, right? So we want to sort all the processing of all the rows and columns in order properly, because you can just do like a bunny hop type thing in that case, and then check it in that case in sorted order. So then maybe we do a reverse. Okay. 1C is pretty big. Yeah, they don't show the one where you could bunny hop it. Okay, I mean that's fine. Longest path in a DAG. I mean that's TP, but is there a way to make sure you only visit the same cell once? Maybe. Well, because of the bunny hopping, the only thing that you're always only looking at the next element that is strictly increasing, unless what do you do? Duplicate entries. We gotta do it quickly. Well, I mean, I think I know how to do it. I'm trying to formulate all the edge cases and try to think. I think the uniqueness one's the tricky one. Maybe. It's the metric, so that doesn't matter. Yeah, I don't know how to handle the unique one, huh? Okay, I think I just need to start programming. Okay, and then basically That's not what I want to do. Something like that, though. It obviously doesn't need to be a collection, but maybe I'm too lazy to fix it. Yeah. Okay, and then now we're just gonna do a dynamic programming thing, right? What am I doing? Is that right? Okay. What am I clicking on? The thing is, you want to cache on. What's my phone? My watch doing? The thing is, you want to cache on not the cell, but actually something like this. Well, maybe +1. Well, this is the row. I just technically I can just write like this. Right. And then otherwise we calculate it. So we have x dot bisect. No, bisect right. So while index is less than row sub x. this one. Oh. Is this how I want to do it? So, okay, so we find a row. I mean, this is silly. Why would I store the same thing? That's why I got confused. Okay, so then now this is the new Y, and then yeah. Okay, yeah. Okay. Now, not to make mistakes on this one, which maybe not. I have to cache this as well. Oh god, this is so quick. I wonder if I'm doing it a little bit weird, or a lot weird. It is actually just +1, I think. Oh no, I'm doing the +1 later, that's why. And then, okay. I'm going to run it real quick without the caching, just to kind of see if it gives me something good. Okay, yeah, of course. Oh, that's fine, right? It's too slow. Really? Should we? Oh, this is, I got this one wrong, because then it gives itself, because I'm an idiot. Okay. Okay, so this is at least good. I don't know how we get infinity, but how do we get it? Infinity for some reason. Oh, at least that's the answer. Oh, because of here. Oh, what am I doing? It's min. Oh, it's max, so set to 0. 214. That looks okay. Whether this is fast enough is another story. Well, this is right now obviously not fast enough, but so we've calculated for, okay, yeah, just want to make sure. I don't know if this is fast enough. So let's see. Let's at least test one big case. Copy and paste is a little bit awkward for this one. Oh, I guess I can just do. I don't know. What's it? What's it to? Yeah. how do I do when? Random.when range. Doesn't really matter, right? I might have negative numbers. It's slow, but this is max case. So let's see if this is good enough. I really don't know if this is good enough, or in terms of speed. But and also maybe correctness. Maybe it's just wrong. We'll see. Doesn't. Oh, okay, cool. Thanks for watching. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem and this contest. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.